In this problem, we're going to take a triple integral and we're going to try to write the order of integration, the dx, dy, dz, dz, dy, dx, in all six possible orientations. So here's the solid that we're integrating over. We have the surface z equals 1 minus x squared on the top, and then y equals 1 minus x on one side, and then we have the xy plane on the bottom and the xz plane on the left-hand side here. So initial notation looks something like this: triple integral over the solid of the multivariate function f of x, y, z. Then we say dv, just because we're not going to pick one yet. Dv could be any of the six, just whichever we decide on. So I'll mention a couple of things along the way. So here's our first example. We've got z equals 1 minus x squared as the surface on the top. Then we've got a plane bounding it on one side, and then the xy plane and the xz plane bounding it on the other side, as well as the yz plane on the back side there. So our first order of integration we're going to try is dy, dz, dx. Now, a couple things that I need to mention before we get started is when you're doing a single integral, you remember that gives you the area under the curve, and we expect our answer to be a numerical value. Well, that's the same as if you were doing a double integral and getting the volume under a surface, and it's no different here. I want this to be a numerical answer when I'm done. Now, the only way to make that happen is to make sure that the outermost limit has constants. If it doesn't have constants, just think about what would happen if you had variables in this outermost limit here. After you did the first integral and then the second, then you got to the third, and then you put your brackets, and then you plugged in the top and the bottom and subtracted. If there were variables in this outermost limit, then you would get variables in your answer, which isn't what we're looking for. So that's one of the key things to remember, is you always want numerical values in this outermost limit. And then another thing we have to remember is the same thing that we know from Calc 1. If I'm integrating with respect to a certain variable, then I have to make sure that I don't have that variable in the limit of integration. That's a bit of a no-no. So with those two things in mind, let's get started. I'm going to look at the outermost limit first. That's usually where I start. I look at the x's, and in this case I'm going to look at the x-axis, and I'm going to see what's the numerical lowest and highest value that x attains. And in this case it's pretty clear, it's from 0 to 1. Now, how did I know that these were 1 right here? Well, just simple algebra. For instance, this line right here, y equals 1 minus x. If the y value, and this is the y-axis, is 0, then the only way that happens is if x is 1. And here, how did I know that this had a height of 1? Well, when x is 0, then z equals 1 minus 0, so it's 1. So I know the x ranges from 0 to 1. And then now I move in and I see, okay, based off of that, as the x's are ranging from 0 to 1, what would the z's be ranging over? And the way I picture this in my head is kind of like one of those old animations that like a computer animation that would fill up a box, but with poor graphics, it would do it slowly. It would go one direction and then another direction, and then it would fill out from top to bottom or left to right or whatnot. It's kind of the same idea. So the z's, as x goes from 0 to 1, would be filling out this region here that I'm showing. So that's going from z values of 0, that's in the xy plane, up until it hits this curve right here, this 1 minus x squared curve. Now, I could say from 0 to z, because it's hitting that curve, but again, that would kind of run into the issue of not having the same variable. But z is 1 minus x squared, so I'll put 1 minus x squared there. Okay, now to fill out the solid, currently I've got shaded in this portion of the solid, just this really just the surface on the side here. Now I need to kind of go left to right to fill out the surface until I bump up against the plane. So what would that be? Well, that would start at y values of 0, and then the y values would increase until they hit the plane. Now I would not say y goes from like 0 to 1, because that would actually give me all these y values. That's too much. I actually want to just go until I bump into this plane right here, which is 1 minus x. So this would be the first representation of the triple integral of the order dy, dz, dx. Now I'm going to go a little quicker through the last five, just now that we kind of have the idea there. Okay, again, I'm going to get in the same rhythm here. I'm going to look at the last variable of integration, that's dz. I notice that z goes from numerical value of 0 to 1. And then based off of that, as the z's go from 0 to 1, I'm going to ask myself, where do the x's go? Well, the x's would go from 0 out until they bump against this curve. Okay. Now, there would be a problem with saying from 0 to 1 minus x squared. That would be that problem I talked about having the same variable in the limit as the variable of integration. But it's no matter, I can fix that. If z equals 1 minus x squared, then x squared equals 1 minus z. So x equals the square root of 1 minus z. Now I don't have to bother with plus or minuses because we're in the first octant here where the x, y, and z are all positive. So I don't need the plus or minus. So it range from 0 to the square root of 1 minus z, and that's still okay to have. And then once again I'm in that plane, then the y's I'll stretch out from left to right and bump up against the plane, and that would be again from 0 up to 1 minus x. And the order of this, you can see how nicely it would flow. If you integrated this with respect to y, then you could plug in a 1 minus x and a 0 and subtract. And so that new integral that you would have for the second one would have x's in it, but that's okay because we're integrating with respect to x. And then we would plug in root 1 minus z into that, but that's fine because in the third integral we'll be integrating with respect to z. So the order is fine. It flows very nicely. All right, keeping on, speeding up a little bit with the third one as well. All right, the y's range again from 0 to 1. That's my outer limit. I keep my eye on that first, from 0 to 1. Then as the y's range from 0 to 1, then the x's are ranging from 0 up until they bump against this line. Not the upper surface anymore, but the x's are bumping up against this line as the y's range from 0 to 1. So that would be from 0 up until, again, you can't say 1 minus x, but since y is 1 minus x, x would be equal to 1 minus y. That would be okay to say. It's the same line, just written in terms of the appropriate variables. All right, now again, going back to that computer animation, I filled out the bottom. I went down the y-axis and then filled out the xy plane. Now it's time to go up and fill out the rest of the solid. And just looking at a couple of representative examples, your z values would go up until they bump their heads on this upper surface up here. But that's constantly changing. Now, what are the z's ranging over? Well, always as low as 0 up until 1 minus x squared. That's that surface on the top rim there. All right, a couple more. dz, dy, dx. Look at the outer limit. It's x, so we go 0 to 1. And then based off of those conditions, what are the y's doing as x goes 0 to 1? Well, it would be going from 0 to 1 minus x for the reasons I said earlier. And again, now that the xy plane is filled out, now we're going to turn our attentions upwards and fill vertically from 0 up to 1 minus x squared there. All right, so we got that one. All right, for the next one, we have the triple integral of f of dx, dy, dz. And by far, this is the ugliest one we've seen to this point, and we'll see why in a second. Starts off like normal. Look at our outer limit. It goes from 0 to 1. The z goes from 0 to 1. And then we look at what y is ranging to and from. Now, it kind of on the beginning, looks like the y's will go from 0 to 1 and kind of fill out that base in the yz plane. And then out you'll come towards us out the x-axis for the last integration. But see, that this guy's going to pose a huge problem, because imagine it being at different spots in the plane. For instance, look at this x value right here. you came out towards us, we would bump into the plane. So we would say 1 minus x would be our our innermost limit of integration. But if we were farther up here and you came out towards us, we would bump into that curved surface right there. So where we are in the YZ plane, moving out the x-axis would give you a different upper limit of integration. So this one's kind of a tricky one. This one, we actually have to break this up into two integrals, and I'll explain why in a second. We'll have another triple integral of f of x comma y comma z dx dy dz. And the reason that there's two of these here is because there's a discrepancy in the innermost limit of integration as to what you're going to bump up against. Now, what's the difference maker? We see this curve right here. That's kind of the dividing line. If we were to figure out where that is, let's set z equals 1 minus x squared equal to, in some sense, or see where it intersects y equals 1 minus x. Now, they both have an x, so I think I'll use that as the loophole to get this intersection line right here. So we'd have x equals, little algebra, the square root of 1 minus z, and then obviously x would equal 1 minus y. Now, a little algebra, I think, would lead to, if we set the square root of 1 minus z equal to 1 minus y, we would get, actually, let's solve this for z. That'd probably be better. Z equals 1 minus y quantity squared. Now, if we're going to take 1 minus y quantity squared, then I might as well just say y minus 1, because the order doesn't matter, because if it winds up negative, I'm going to square it anyways, so it'll be positive. So y minus 1 looks a little bit better. And then it'll be negative, and then it'll be, let's see here, plus 1. So you can check my algebra if you want to take an extra second to do that. But if you look at this picture, this is really what's going to tell the story. This is in the YZ plane. This is a parabola that opens downward. This then moves right 1 and up 1. So at 1, 1, we'll have a downward opening parabola. It kind of looks like this. And it extends no farther than 1, so I'll just go ahead and close it off here. And it goes no higher than 1, so I can close it off there. If you can picture yourself in this physical three-dimensional space, and you walked over and you kind of got a lower angle of the picture, can you kind of see this would be the dividing line between this right here, which would be the curved surface, and this region right here, which would be the plane. That would be the two things that we bump into in trying to figure out this dx. The x's go from 0 up until these two different things. So I'm going to do two separate triple integrals just based off of these two separate ranges for x. So we'll do the one where you bump into the surface first. So let's see, the z's will still go 0 to 1. That doesn't change. But notice the y's, and I'll try to color code these. I'll do this one in yellow. The y's only go from 0 up until this curve right here. They bump into whatever that curve is. So they would go from, let's see, the z's go 0 to 1. The y's go from 0. Then I just need to go find whatever that curve was. That's well, that's this curve right here, isn't it? Now, unfortunately, I would wish I could say 0 to negative y minus 1 squared plus 1, but that's in terms of y, unfortunately. So I have to do a little algebra, which I'm not too excited about, but I think we can do it. Let's see here. You'd have z minus 1 if you subtracted the 1, and then took care of the negative. That would be 1 minus z. Then we'd have to take a square root of that, and then we would have to add 1. So I did skip a little algebra there, but that would be y at the end of the day. So 1 plus root 1 minus z. Sorry, it's getting a little messy here. This, like I said, this one was ugly. And then as that happens, and you're in this part of the YZ plane, as the points come out towards us on the x-axis, the x's will range from 0 up until this surface, the the 1 minus x squared. Unfortunately, I can't say 1 minus x squared because that has x's, so I will say the square root of 1 minus z, just simply solving that relationship for z instead of being in terms of x. Ugly, 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 I understand that, but it's what we have to do here. All right, and then for the other one, I'll color code that with maybe green. All right, now we're in this region here. The z's still go 0 to 1, but as the z's are going from 0 to 1, the y values are going from this curve, that 1 plus root 1 minus z, from that curve up to 1. They're bumping up against the right-hand side and hitting a constant value of 1 each time. And then as they're doing that, then the x's, as you come out towards us, will be up to the plane, 1 minus x, but unfortunately that has an x, so we'll rewrite that as x equals 1 minus y. Okay, not pretty at all, not pretty at all, but you would have to take both of these independent integrals and then add the results together, which that's perfectly allowed to do. All right. Let's see here. Looks like we got one more. Let's push on through. Dx, dz, dy. Dx, dz, dy. So here we go. Y is the outermost limit. They go from 0 to 1. As the y's are going 0 to 1, then the z's, as the y's are going from 0 to 1, then the z's would go from, let's see here. It looks like we got that same issue again, having the x as this innermost limit here. We're going to run into that same issue of the surface versus the plane. So again, not too excited about this, but we do what we got to do. We got another triple integral here. X comma y comma z, dx, dz, dy. All right, let's see here. Let's try to cheat as much as we can. The z's, if we have that same, we'll draw that same picture again here. Okay, we have the surface on this side and the plane on this side. If you're just kind of taking a side view of this guy here, then let's see. Let's do again the surface one first. The y's go 0 to 1. Y's go 0 to 1. As the z's go, look at this picture, this diagram right here, go from the curve up to 1, from the curve up to 1. But here's that curve. Here's that curve we were referring to, and it's the nicer version this time because we don't have to put it or solve it to be in terms of z. I like it in terms of y the way that it initially was, and so we'll say from the curve for the surface one, from the curve negative y minus 1 squared plus 1 up to 1 until it bumps its head on the ceiling up here. I'm doing the yellow one here. And then it's pretty easy for the last step. The x's come out towards us from 0 up until this surface here, the 1 minus x squared, but I can't say x because it's dx, so I'll say the square root of 1 minus z. All right, and then I'll do the one on the other half with the plane down here in green. So for that one, the y's go from 0 to 1, and the z's will go from 0 up to the curve, not from the curve to 1, but from 0 up to the curve. From 0 up to negative y minus 1 squared plus 1. And then the x's will go from the yz plane out towards us until we get to the plane, which is 1 minus x. But I can't say 1 minus x. I'll write x equals 1 minus y. 1 minus y. So there we go. We have to add those two together. Now the last two I know were not very fun, but we made it. We did all 6 orders of integration there. Now just something a little extra here. This is a little extra tidbit. We know from Calc 1, if you're doing just a single integral, and you let the integrand just be the number 1 and the 1 only, you don't put a function on the inside, you just let it be 1, and you get x from a to b, so you have b minus a. I don't know if you ever realized this or not, but when you integrate 1, what we got was the length of the interval from a to b. You got b minus a. If that's from 2 to 7, your answer would be 5, right? Because it would be a length of 5. Well, in Calc 2 or Calc 3, when you learned about double integrals, you took a double integral of 1. Then what we came up with was not the volume under any surface. This was just a function 1. We actually got the area of R. Where it normally gives you volume, in this case it gives you area. Well, in Calc 3, when we learn triple integrals, you take the triple integral of 1, you let that function just be the constant 1. What you actually get is volume, the volume of that solid there. So it's kind of interesting. So just a quick little side note, I actually went through and worked out the algebra. If we took that same triple integral, I'll just pick one of the easier of the two, or the 6 triple integrals. I actually just went through the algebra where the integral was 1 and not some random function. It took the first integral, and then the second, and then the last integral was just a single Calc 1 type of integral. And I got 4/10. And that answer is pretty interesting because if you look, this is a 1 by 1 by 1 type of a shape, or it's like a 1 by 1 cube trimmed down a little bit. And you can see this plane in effect cuts that cube in half, which would automatically put it at zero point 0.5 cubic whatever your unit is. And then you slice off a little bit more because of this curved surface. So a volume of zero point 0.4 cubic centimeters or cubic inches or cubic feet or whatever makes perfectly good sense, when you just think about the geometry of the solid.